Throughout the world, in every place where land meets sea, waves are continually changing the shoreline landscape. There is a wide variety of coastline forms. Some, like the one shown here, are comprised of solid rock, others of less resistant gravel and clay. But every coast is shaped primarily by the work of the waves, wave after wave, year after year. To investigate the effect of waves, let's look first at some small terraces along the shores of a reservoir. These terraces lead like steps up the bank from the water. Terraces along a coastline are formed like this. First, the waves cut out sand and other materials to form a wave-cut cliff and a small platform. Over a long period of time, the land may be uplifted several times to leave a series of cliffs. At low tide, we can see the new rock platform being cut into the face of the old terrace at the left. During storms, the waves will break directly against the face of the cliff. The older high terrace was itself formed by wave action at sea level and has since been uplifted by forces of diastrophism. When the new beach begins to form, it may be made up of large rocks. This is known as a cobble beach. But with the continual action of the waves, these rocks will be worn down to small stones and pebbles. In time, the stones and pebbles will be worn by the waves to sand. Since waves are so important in the creation of coastline topography, let's learn more about them. We can do this with a wave tank. When the wind blows, ripples begin to form. Then the ripples grow larger and become waves. The waves travel along the surface of the water. But in spite of its apparent forward motion, the water itself moves in circular orbits. We can see this clearly if we put a cork in the water. The cork moves with the particles of water around it, in circles, as wave after wave passes by. Watch. It is only when the waves meet the shoreline and collapse that the water spills forward. When this happens in our wave tank, the erosive action of the water is clearly seen. Watch how the turbulent action of the breaking waves erodes the bottom. In nature, the power of waves, even ordinary waves, can be enormous. And during a storm, when the waves are strongest, they may exert a pressure of more than 20 tons per square yard. With this kind of force, cliffs like these may literally be pounded apart. These fallen pieces of rock were broken off and may be tossed into the waves and battered against the cliff. So over the years, the coastline changes. More rocks are broken off until entire areas of the cliff may be cut away, leaving spires of the most resistant rock. In some places, the natural rock may be worn away in unusual patterns, leaving natural bridges, grottos, or caves. But in time, these too will be broken down by the ceaseless work of the waves. Still another factor in shaping our coastlines are rivers, which carry sand, silt, and other sedimentary materials into the sea. These materials may then be transported along the coast by strong ocean currents. Some of the sand, which is carried into the sea by rivers, is deposited on the beach. But most of the sand and finer sedimentary materials are deposited underwater on the ocean floor. In shallow water, wave action extends clear to the bottom, forming ripple-like patterns in the fine sediment. However, the slow movement of this clump of seaweed shows that the actual water movement close to the bottom is very slight. Hydrographic models of near-shore areas show terraces, valleys, and mountains in the landscape beneath the sea. Underwater canyons like this one are continually being filled with deposits washed down from the surface. But peaks are also being formed underwater. They are created by the same forces of diastrophism which uplift the land elsewhere on the crust of the earth. Millions of tons of sediment are washed into the sea each year to pile up on the ocean floor or to be carried onto the coastal beaches. The sand on a beach is continually moved along the coast by the action of the waves. Here, the moving sand of the coast is obstructed by a peninsula. This kind of pointed land spit may occur where the longshore current meets a flowing river. The two forces work together, one from each side, to shape a peninsula. Where the longshore current meets a slow-moving river, the sandbar may almost close the river's mouth. Notice the small opening at the lower end of this long, narrow sandbar. Here, the current is piling up sand along a man-made causeway. Where there are no obstructions, the sand will be moved straight along the coastline in the direction of the prevailing current. But currents and waves are not the only forces that reshape a coastline. Over long periods of geologic time, the forces of diastrophism may cause a coast to sink. As the sea covers the submerged land, the resulting coastline may be highly complex, with islands, winding inlets, and irregular bays. This is particularly true of a submerged river valley like this one. The sheltered area here is used to protect the man-made oyster beds seen in the water. On a contour map, we can see what happens as the land sinks. Lower levels are successively submerged. Higher levels remain as irregular land areas. Over thousands of years, submergence may continue. The highest contours of the land may be left as islands in the bays. And the size and shape of the islands may continue to change as the land is further submerged. If, on the other hand, the land is uplifted, the result is an emergent coastline, like this one. So these forces, diastrophism and erosion by waves, currents, and rivers, are continually affecting coastlines. The topography of a coast is a pattern of constant change.